Okay, we're on the air again. Are there any questions? Last time we were talking about, we're still on the theory of the birth and death process, and I gotten to the point where, based on some postulates, I had derived equations 2.3. So this is the key starting point. So we have a system in which there's a population, and the population grows and shrinks essentially one step at a time. And we made some assumptions about how those steps occur, and then we got some equations for the probability that the system is in state J at time t. By state J, that means the population size is J, or you're at level J. Now, the equations were that the derivative with respect to t of pj of t is given by the following. Lambda sub j minus 1 p sub j minus 1 of t plus mu sub j plus 1 p sub j plus 1 of t minus lambda j plus mu j pj of t. So we have this set of simultaneous differential equations. And the lambdas and the mu's represent the so-called birth and death coefficients. And they correspond, or they relate to the probabilities that births or deaths occur in little intervals of time. And what we said was that, that these probabilities are proportional to the length of the interval. The lambdas and the mu's are the proportionality constants, and we're going to allow them to depend on the population size at the beginning of the interval. So that's what we did, and we went through all of this, and we got this result based on the assumption that we had this little error term. The error term is the probability of multiple births and deaths in a little interval of length h. And we said that if we took that error term, which we called little o of h, and divided by h, and took the limit of that as h goes to 0, then we would get 0. And that was necessary in order to be able to write these equations. So at the outset, it was not clear what this meant, or if it meant anything, but we saw that if we made this assumption, then that led to these equations. And then we looked at those equations for three particular cases. The first one was the pure birth process, an example of a pure birth process, and in fact what we derived was the Poisson distribution. And then we looked at the pure death process, and for that we derived what turns out to be a binomial distribution. And the binomial distribution, let me step back a minute for the pure birth process. For that case, we found that the solution implied for the particular assumptions we made for the lambdas, that the times between births were exponentially distributed. And then for the pure death process, the example we took was where the death coefficient was proportional to the population size. And in that case, we found that the solution that we got was the same as we would have gotten if we had assumed that the population size corresponds to lifetimes, all of which are independently, identically, exponentially distributed. So we got this exponential distribution in there. And then we looked at the third case, which was mathematically a little bit more difficult, because when we have pure births and pure deaths, the equations can be solved recursively or iteratively by successive substitution, because in a pure birth case, all these guys are 0 by definition, and in a pure death case, all these guys are 0 by definition. So that makes the equation simpler. In the birth and death case, then these guys in general are not 0, so that means that the equations are more difficult to solve. You can't solve them by successive substitution, but we looked at one single case, and for that case, we were actually, a simple case where there were only two states, and for that case, we were actually able to solve the problem, get a solution, and then we looked at the properties of the solution. Now, in the case of a pure birth process, there is no equilibrium solution, because as time goes to infinity, if there are only births, then the state of the system goes to infinity. In the case of the pure death process, there's an equilibrium solution, but it's trivial, because in that case, the only thing that can happen is deaths, and eventually everybody's dead and you're in state zero. So the only interesting case, I shouldn't say only interesting case, but the case that we're looking at now is the birth and death case, where there are births and deaths so that the system can oscillate from state to state. And for that case, we actually solved it, and we got an explicit solution, and we found that two things were true. One is that when we found the probabilities, we could take the limit of the probability of being in state J at time t and take the limit of that as t goes to infinity, and the result turned out to be something that was independent of the initial state, and we call that P sub j. So in other words, the limiting probabilities exist in this particular case. And that's not surprising, because you would expect that if you have a system that jumps back and forth from state to state, that in the long run, as t goes to infinity, the probability that you would be in any particular state would not depend on where you were at time zero, because it's an infinite time away, so that you would expect you would have a limiting distribution. And in fact, the limiting distribution is the one that you would typically be interested in, because in applications, you're not really ordinarily concerned with the probabilities of being in any particular state at a specific time t, but you're concerned with the system after some long time in which the initial condition is worn off and you have basically a random state. So this is really what you're generally interested in, but it looks like it's in general very difficult to find, because first you have to solve the equations, then you have to take the limit as t goes to infinity. Now we also saw for the simple two-state birth and death process, we considered that the derivative of pj of t, that its limit was 0. Of course, that's not surprising either. It would be surprising if any other result were true, because what this says is that if the probabilities approach a constant, then you would expect that the derivatives would approach 0. So this is not surprising, and in fact, my claim now is that we have justified initially assuming that this is true. So here's the idea. Instead of, in general, finding the solution to these equations, the equilibrium solution, by solving the equations, now remember that's in general a very difficult job, and then taking limits, what I'll do is I'll assume that there's an equilibrium condition, because it makes perfect sense under ordinary conditions. So I'm going to assume that if I took the limit as t goes to infinity, that limit would go to 0, and these probabilities would, the dependence on t would disappear, and I would get a set of equations which don't have any t in them. So let's do that. Let's assume that as t goes to infinity, these limits are as stated. So that means this would say 0 is equal to lambda j minus 1 pj minus 1 plus mu j plus 1 pj plus 1 minus lambda j plus mu j pj. So now we have a set of algebraic equations. These are just linear difference equations for the p's in terms of the lambdas and mu's. So let's see if we can solve that and get something that comes out of here that looks like it makes any sense. And the answer obviously is yes, that's what's going to happen. So first of all, let me bring this to the left-hand side and rewrite this as lambda j pj plus mu j pj is equal to lambda j minus 1 pj minus 1 plus mu j plus 1 pj plus 1. And this is going to hold for j equals 0, 1, 2, and so forth. Okay, so now let's solve these equations. But this is easy, it turns out, because let's start with a case where j is equal to 0. So when j is equal to 0, the left-hand side gives me lambda 0, p0. This term is 0 because when I'm in state 0, the probability of a death is 0. I don't allow the system to go into a negative state. So when j is equal to 0, that term is 0. When j is equal to 0, that represents a negative state, so of course that probability is going to be 0. When j is equal to 0, this is mu1. So we get mu1 p1. Okay, I can solve that now, and I can say that's going to give me p1 is equal to lambda 0 over mu1 p0. Good. What's the next equation? Yeah. Question?
Isn't that equation saying rate up equals rate down?
Which one now?
Mu 0 p0 equals...
That's right. That's what I'm getting to, is that if you remember, okay, the question was, doesn't this say rate up equals rate down? And the answer is yes, these equations will say rate up equals rate down. And in fact, this equation right here says rate out equals rate in. So we started the course with this intuitive argument that says we should have rate up equals rate down, but we didn't know under what conditions that would hold. And then what we did is we looked through simulation, we looked at a particular case, and we saw that the rate up equals rate down equations agreed with simulation under some assumptions and not under others. So we want to now run that down. So the answer is, when I get done with this, this will say that a sufficient condition for rate up equals rate down is this stuff right here. And then the question is, what does that mean? And the answer will be, if the underlying variables are exponentially distributed, then this will be true, then rate up will equal rate down. And if they are not exponentially distributed, then in general it's not true, although it might be. In a particular case, that's a theorem that's called insensitivity, and we saw that in the case of the Erlang loss model for the service process. So now what I'm trying to do is put all these things together so it all comes full circle, and then once this is understood, then we can go back to the original models and understand them better. Okay, so this says then that the rate up from state 0 is equal to the rate down from state 1. We could interpret it that way. What's the next equation? Let's see. I'll write it here. Never have enough space. Okay, I think I'll write it here. Okay, now if I go back to this equation, or excuse me, this equation, and I set j equal to 1, what I get is lambda 1 p1 plus mu2 p2 is equal to lambda 0 p0 plus mu3 p3. But we already know that lambda 0 p0 is equal to mu1 p1. So let's see, what do we do here? Lambda 0... something's wrong here. What did I just do? I'm in here and I'm plugging in j equals 1. So that's going to be a 1. This is going to be a 1. When j equals 1, that's a 0. This should be a 2. Okay, makes sense now. Okay, now we already know that lambda 0 p0 is equal to mu1 p1. So I can cancel the lambda 0 p0 with the mu1 p1. And so what I'm left with is lambda 1 p1 is equal to mu2 p2. Okay, so what's the next equation? I'll do one more. The next equation from here is lambda 2 p2 plus mu2 p2 is equal to lambda 1 p1 plus mu, let's see, mu3 p3. And again, since lambda 1 p1 is equal to mu2 p2, those terms cancel out, and I find that lambda 2 p2 equals mu3 p3. So you can see that the general expression here is going to be lambda j pj is equal to mu j plus 1 pj plus 1. Okay, so I can interpret this as rate up equals rate down. And similarly, over here, I can interpret this as rate out equals rate in. In other words, for each state, the rate at which I leave the state by births or by deaths is the rate at which I enter the state from below plus the rate at which I enter the state from above. So those were the interpretations I gave, and now we see that, and that's how we started. And now we see that in general, if there's a limiting distribution, and if that limiting distribution is attained without oscillating, attained in the ordinary way that you would expect intuitively, then that means that this derivative goes to 0 as t goes to infinity, and that means that these equations become the rate up equals rate down equations that we wrote originally, and there they are, and we can solve them. So in fact, if we solve them, you can see that I can get each one in terms of the other. Here's P1 in terms of P0. I can get P2 in terms of P1 and so forth. And in fact, I can get the general solution, Pj is equal to lambda 0, lambda 1, up through lambda j minus 1, divided by mu 1, mu 2, up through mu j, P0. And then we simply find the P0 by requiring the probabilities to sum to 1. And the question is then whether or not that infinite series converges depends on the particular lambdas and the mu's that we choose. Now this is in the book. Let me see where this is. There's a section on statistical equilibrium. Then there's a theorem on page 22. Theorem, page 22. And the theorem states under certain conditions that the equilibrium exists and is given by this. So in order to have an equilibrium solution, then it depends on the requirement. What we need to have here is we want P0 plus P1 plus P2 and so forth. That has to add up to 1, which means that when I add these things up, this infinite series must converge. So if it converges, then we have this solution. If it doesn't, then we say we do not have an equilibrium solution. Now, that's a theorem, and all I did was say that if I'm simply willing to assume what is intuitively reasonable, namely that the equilibrium solution exists and that and that in the limit as t goes to infinity, the derivatives go to 0. If I'm willing to assume that, then I get that answer. And that allows me to write down an explicit solution. Okay, so now we know that if the postulates for the birth and death process are met, which essentially is this piece right here, if those things are met, then we can write rate up equals rate down. And if they're not met, well, then maybe we can or maybe we can't. We're not guaranteed. In fact, usually we can't. So that means that the program now is to better understand what this thing means right here. All right, so what I want to do is I want to now go back and say, let's look at the exponential distribution and see what the properties of the exponential distribution are. In particular, it's going to turn out that this is a key property. And what that means is then we'll be able to say, if the underlying random variables that drive the birth and death process are exponentially distributed, then the conditions for the birth and death process will be met. That means that the state probabilities are given by the rate up equals rate down equations. So we can either work directly with these equations, or we can plug into this formal solution, although it's usually easier to work directly from here. So now I want to start looking at the exponential distribution. Okay, so are there any questions about the big picture here? Now, at this point, I think that the course is veering off a little bit to be more concerned with the theory of stochastic processes than it actually is when we get into it more deeply. But I think it's necessary at the beginning. Okay, so the stuff I'm doing now is standard stuff from the theory of stochastic processes. Okay, so let's look at an exponential variable. Okay, so I'm going to erase this. So the exponential stuff, basically in queuing theory, we have several related questions. Are the random variables exponential? If not, what do we do about it? Does it matter? If yes, well, why should they be exponential? And because remember, we're trying to make a model of reality. So we want to understand what the mathematical properties of the exponential distribution are and what its physical properties are. And one of the physical properties we already have, which is a characteristic memoryless property. And you already know that that's a little bit sneaky because you looked at the waiting time paradox and you see that it produces things that are counterintuitive. But nevertheless, it represents the best model of complete randomness unless you have evidence to the contrary. And I think I've convinced you of that, and I'll try and continue to convince you of that. Okay, so first of all, I'm going to look at an exponential variable like a lifetime, for example, a service time, or an inter-arrival time. So I'm going to use a lambda as my parameter, which I usually use for arrival rates. So let's say we have this process in which we're waiting for something to happen. We're waiting for an arrival to occur or a birth to occur. And so here is time t, and here's time t plus h. Now, if the lifetimes, this is time 0. If the lifetimes are exponentially distributed, in other words, the times between arrivals are exponentially distributed, then by the Markov property, which we've already proved, that means that the absolute value of t doesn't matter. There's no memory. And so if I wanted to, I can call that 0 and that h, because the length of time that has elapsed since the last event at time t is irrelevant because the process continually renews itself, starts over again. So here's time 0, here's some time later h. And what I want to know is this. I want to know what's the probability that the number of births between t and t plus h is greater than or equal to 1. I need another parentheses here. Not there, here. In other words, capital N represents the number of births in the interval between t and t plus h, which is now, by our argument, the same as the number of births between 0 and t, because it doesn't matter what happened between 0 and h, because it doesn't matter what happened between 0 and t. So I want to calculate this probability. Now, by assumption, the times between these births are exponentially distributed with some parameter, which I'll call lambda, which means that what I'm asking for is if the number of births in that interval is greater than or equal to 1, that's 1 minus the probability, or that is 1 minus the probability of being greater than 1. In other words, if I have at least one arrival in here, then the time to the first arrival measured from here must be less than h. So if it's exponentially distributed, that probability is 1 minus e to the minus lambda h. Okay, that's the distribution function for the exponential variable in which the value of the parameter is h. Okay, now what's that? Now let me remind you, trying to find something here that writes without running out. Let me remind you from calculus or someplace along the line that e to the x can be expanded as 1 plus x to the 1 over 1 factorial plus x to the 2 over 2 factorial plus x to the 3 over 3 factorial, and so on. Okay, so with that, that means that this thing right here can be written as 1 minus, all right, now e to the minus lambda h is 1 minus lambda h plus lambda h squared over factorial 2 minus lambda h cubed over factorial 3, and so forth. Or in other words, it's equal to lambda h. Those ones cancel. The minus sign becomes a positive sign. And what am I left with? What I'm left with is terms that all have an h in them to the power 2 or higher. H squared, h cubed, and so forth. Now, if I take each term, which has an h to the power 2 or higher, and divide it by h, then the result in the numerator is going to be a term that is going to have h to the power 1 or higher. So when I let h go to 0, the whole thing is going to go to 0. So in other words, this expansion gives me lambda h plus some stuff, which has the property that if I divide by h and let h go to 0, all the stuff goes to 0. So the conclusion is that the probability that I have at least one birth in this interval of length h, regardless of where the h is located, if the births occur according to a Poisson process, is lambda h. In other words, it's proportional by the arrival rate to the length of the interval plus an error term, and the error term has the property that if I divide it by h and let h go to 0, the error term goes to 0. So this is exactly what we need for the postulates for the birth and death process. Okay, does this make sense? Any question here? Okay, that's the probability that I have at least one birth. Now, what's the probability that I have exactly one birth? Okay, so now I want to calculate the probability that the number of arrivals between t and t plus h is exactly 1. Here I calculated the probability it was greater than 1. And the way I'll do that is I'll say, well, let's see. First of all, let me draw a diagram here. Here's 0. Here's h. I want to have exactly one arrival between 0 and h. Okay, so how can I do that? That means that at some time u, between 0 and h, there must be the first arrival, and between u and h, there must be no additional arrivals. Okay, so what's the probability of that? So now we go back to your elementary probability theory. First of all, what's the probability that at time u I have an arrival if the inter-arrival times, if this interval is exponentially distributed? Well, that would be the density function of the exponential distribution evaluated at u times du. So lambda e to the minus lambda u du, that's the probability that I have an arrival, my first arrow occurs between u and u plus du, or essentially that my first arrow occurs at u. Now, since I have to have exactly one arrow between 0 and h, and the first one occurs at u, that means that there must be no other arrows between u and h. What's the probability of that? Well, if the times between arrows are exponentially distributed, then the probability that there is no arrow in the interval of length h is e to the minus lambda h minus u. And now I have to add that up or integrate over all possible values as u ranges from 0 to h. That's the theorem of total probability. So this is the integral from 0 to h. And now I have to evaluate that integral. Okay, so let me go through that argument again. This is a classical probability argument. I have a process in which these arrows are generated with exponential inter-arrow time. So I'm starting here at time 0, and I want to calculate the probability that between 0 and h, I have exactly one arrow, exactly one birth. I've already calculated the probability that there's at least one. Now I want exactly one. Okay, that probability is the probability that my arrow occurs at time u and that nothing else occurs between u and h for every possible value of u between 0 and h. So I first of all calculate the probability that an arrow occurs at time u. This is, of course, right here. That's the density function evaluated at u du, which we interpret as the probability that this random variable, whose density function is f, that's the exponential density function, a continuous random variable, takes a value equal to u. Okay, this is an essential argument of elementary probability when you're discussing continuous random variables. Now, given that the first arrow occurs here, we want no other arrow to occur after u and before h. So that's the probability that in this interval of length h minus u, I must have no arrow. But since these arrows are exponentially distributed, that probability is e to the minus lambda h minus u. So this is the probability that the first arrow occurs at u. This is the probability that no other arrow occurs between u and h. This adds these probabilities up for every value of u between 0 and h. So now it's a matter of evaluating this integral. But this is easy because, first of all, I'll take out the lambda, and I'll take out the, let's see, what else I want to take out. I'll take out the e to the minus lambda h. And what I'm left inside is e to the plus, let's see, the integral from 0 to h of e to the plus lambda u, e to the minus lambda u, du. Of course, the e to the plus lambda u and the e to the minus lambda u cancel as 1, and this integral simply becomes h. So my answer is lambda h e to the minus lambda h. Okay, so now we know that the probability that the number of births between t and t plus h is exactly 1 is equal to lambda h e to the minus lambda h. But this can be expanded because, remember, e to the minus lambda h is 1 minus lambda h plus lambda h squared over factorial 2 minus plus and so forth. Or in other words, it's equal to lambda h, and all the other terms are going to have h squared in them or higher. And if they have h squared in them or higher, that means that if I divide by h and take the limit as h goes to 0, I'm going to get 0. So everything else is little o of h. So the probability of at least one arrow is lambda h plus little o of h. And the probability of exactly one arrow is lambda h plus little o of h. So that means, yeah, question?
Sorry, just one more time, explain how you're doing the O of H equals.
Okay, what I'm doing is, question is, where does this O of H come from? Okay, remember that I got this result right here. This is what I get when I evaluate the integral. Then I expand e to the minus lambda h. Okay, 1 minus lambda h plus lambda h squared over 2 minus lambda h cubed over 3 and so forth. Okay, now if I multiply that out, that's going to give me lambda h minus lambda h squared plus lambda h cubed over factorial and 2 and so forth. So except for the first term, all of the other terms are going to have h's to the power of 2 or more. Now, if they have a power of 2, then if I divide by h, the remainder has a power of at least 1. If it has a power of at least 1, if there's at least an h to a power 1, then when I take the limit of that as h goes to 0, the term is going to go to 0. So you remember what I'm doing is I'm dividing each of the terms in this expansion by h. So when I divide by h, if the numerator has h squared in it or higher, when I divide by h, I still have an h in the numerator. And then when I let h go to 0, the whole thing goes to 0. So all this stuff goes to 0 as long as the terms up here are squares, cubes, and so forth. So it was the same argument I made over here. Over here I said, okay, what I'm going to do is recognize that this is 1 minus 1, that's 0. This term is the lambda h. What's left? Well, there's lambda h squared over 2, lambda h cubed over factorial 3, and so forth. All of those terms have the property that if I divide by h, then this term would become an h in the numerator. And the next term would have an h squared in the numerator. Next term would have an h cubed in the numerator. So if I then took the limit as h goes to 0, the result would go to 0, which means by definition, all that garbage is what's called a little o of h. Because little o of h means it's shorthand for anything that has the property that if I take whatever it is and divide it by h, and then take the limit, everything goes away to 0. And that's what was necessary in order to write our differential equations. Because when we got all done, we had an O of h over h, and we took the limit as h goes to 0 to get to a derivative. When we took that limit, we said, okay, we're going to make the O of h have the property that if I divide it by h, it goes to 0. The question is, are there any such random variables that have that property? And the answer is, well, yes. If the random variable is exponentially distributed, then it has that property. You still look puzzled there.
Well, the problem that I'm having is that you just said the reason why you're condensing this down to h is because it has the property such that when you divide by h, it goes to 0. But that's what you're trying to prove.
No. Okay, what I'm trying to prove is, let's start this again. We wrote some differential equations. We wrote some equations. When we wrote the equations, we aggregated a whole bunch of probabilities that corresponded to multiple events. And we said that, well, that's some garbage. We don't know what it is. We called it little o of h. Then we saw that when we took the limit as h goes to 0 in order to write a differential equation, one of the terms had that little o of h over h in it. So we had to say that in order to be able to get these differential equations, the term that's called little o of h over h must go to 0 as h goes to 0. Does it? Well, we assumed it did for the purpose of writing the differential equation. Because if it didn't, then we were nowhere. So we said, okay, let's suppose that these errors have the property that whatever they are, as h goes to 0, they go to 0 faster than h does, meaning the ratio of the formula for the error divided by the length of the interval h has, when you get done dividing it, has in the numerator h or higher order. Now, having done that and then said, okay, if we do that, then we get rate up equals rate down, and everything makes sense. Now we want to go back and say, okay, it makes sense if we have this little o of h stuff, but do we actually have that? So now I'm saying, okay, now I'm going to take a different point of view, and I'm going to say, suppose that I look at a process in which the times between events are exponentially distributed with what we'll call a parameter we'll call lambda. So now I'm assuming they're exponential, and I'm going to show that if they are exponential, then the property that we need to write the differential equation is satisfied. Now, I could skip all of this because if you just take my word for it, we're never going to use it again. This just gives you an idea of what the exponential distribution does, why it appears all the time, and why it's surprising when it turns out to be unnecessary. Okay, so I want to justify my assumption that the probability of having multiple births and deaths in a little interval of length h is so small that can be viewed as something that goes to 0 faster than h does, so that I can ignore it, because when I take this limit, it goes away. Because it's conceivable that there could be no such process that has that property. So we would have derived differential equations that are very nice, but the they only apply to a vacuous case. Or it could be that there are random variables or processes that have this property, but they're not realistic descriptions of anything. So to the extent that the exponential distribution is a realistic description, then this works. Okay, so the first thing is we want to calculate the probability that if we have exponential inter-arrival times, that the number of arrivals in an interval between t and t plus h is being more than 1, at least 1, is given by lambda h plus all this error that I can ignore. How do I do that? Well, I simply say that if there's to be at least 1 arrival in this interval, that means that the time from here to the next arrival must be less than h, because this interval is of length h. Okay, now the probability that it's less than h is the distribution function for the exponential if the random variable is exponentially distributed. Okay, so this probability is 1 minus e to the minus lambda h. Then I expand my e to the minus lambda h in a power series, and I say that what I get is the first term is lambda h, and the second term is a term that has h or h squared or h cubed and so forth, has h squared or higher in the numerator. So all of these terms, if I divide each of them by h, then one of the h's would cancel out, but there would still be 1 in the numerator. And therefore, if I took the limit as h goes to 0, I would get 0, which means that all of this stuff here, all these terms, can be said to be O of h, because they have the property that if I take them and divide by h and let h go to 0, they go to 0. So that means that the probability of having at least 1 birth in this interval of length h, regardless of where t is, if these intervals are exponentially distributed, is given by lambda h plus little o of h. The lambda is the parameter of the exponential distribution, the h is the length of the interval, and the O of h is all of the stuff I can ignore because it has the property that when I divide it by h, it goes to 0. Okay, so this is the probability of at least 1. Now I want the probability of exactly 1. What's the probability of exactly 1? So now I make this probability argument that's saying, well, if there's exactly 1, then it must occur at some time in the interval, call it u, and if it's exactly 1, there must be no other between u and h, because if there was some other one, then there would be more than 1. Okay, so what's that probability? This is the density function for the exponential. So this is the probability that the first arrival after time 0 occurs at time u. This is the probability that between u and h, no other arrival occurs. Add them up over all possible values of u between 0 and h, and that gives me this integral. Evaluate the integral, and I get this answer right here. Expand the e to the minus h, and I get the same thing I had before, which means that I can ignore all of the stuff except for the first term, lambda h. All the rest of it is O of h, and so I just write it as O of h. Okay, so now what I want to calculate is the probability that I want to say that the probability that the number between t and t plus h is greater than or equal to 2 is equal to the probability that the number between t and t plus h is greater than or equal to 1 minus the probability that the number between t and t plus h equals 1. Okay, why is that? Well, just put this thing here on the left side of the equation, and what it would say is the probability that the number that arrived between t and t plus h is 1 plus the probability it's greater than or equal to 2. That's the same thing as the probability it's greater than or equal to 1. Okay, that being the case, what is this probability? Well, this probability right here we already saw is 1 minus e to the minus lambda h. And this probability we already saw is lambda h e to the minus lambda h. And now I simply expand those, just as before. So when I expand them, what I'm going to get is the term for greater than or equal to 1, which is lambda h plus little o of h, minus the term for let's see, get this straight here. I'm calculating the probability of at least of 2 or more arrivals. Okay, so that's going to be this value right here, which is that, minus this value right here, which is that. So the lambda h and the o plus the little o of h is going to cancel out, and what I'm going to get is little o of h. In other words, I expand this, all the terms cancel except terms that have h squared or higher in them. Okay? What is this one right here? Okay, that's the greater than or equal to. That's this. Okay. What's...
You've got lambda h plus o of h minus lambda h plus o of h. Would that 0?
Yeah, but there's all that other stuff, which is o of h.
No, because both sides have an o of h.
Okay, let's work this out. 1 minus, okay, what do we have here? Let's see, this is going to be 1 minus lambda h plus lambda h squared over factorial 2 minus lambda h cubed over factorial 3 plus and so forth. And then we have minus lambda h times 1 minus lambda h minus plus, let's see, minus lambda h, 1 minus lambda h plus lambda h squared over factorial 2 minus lambda h cubed over factorial 3 plus minus and so forth.
I got confused by the fact you used o of h in both
Right.
sides.
Right. So what's going to happen here is the ones are going to cancel. Then I have a minus lambda h. This is a plus lambda h. That's going to cancel. Then each term is going to cancel. And all it's going to be left is stuff, I hope, stuff with h squared or higher in it. So when you get all done with this, the only thing that's left is stuff which is going to go to 0 as h goes to 0. At least that's, let's see, if I haven't made a mistake, that's what should happen. Okay, so the bottom line is that we just proved that the probability of a single birth in the interval of length h is lambda o of h, and the probability of multiple births is o of h. And that was one of the requirements for the birth and death process. Okay, but here we're only looking at a single random variable. What we want to do is we want to be able to combine births and deaths and show that not only if the births are exponentially distributed, if the inter-arrival times are exponentially distributed, then we have the property for the births. And if the deaths are exponentially distributed, then we have that property for the deaths, but we must have them combined. And furthermore, in our queuing context, we're going to have random variables that are racing against each other in the following sense. If I look at such a system, the time from now to the next transition is the minimum of a whole bunch of times. It's the minimum of the time until the next event. The next event could be a birth or it could be a death. So I have to look at these exponential random variables competing with each other and show that in the aggregate you still meet these conditions. All right, so all I've done now so far is looked at a process with a single exponential inter-event time. Okay, so now I want to look at a few other properties of the exponential distribution. And in the end, all of these properties come down to the Markov property. Okay, so suppose that I have a bunch of exponentials. So let's say, okay, I'm not sure we're going to make it through here with these things. Suppose that I have these exponential variables. I'll call them xi, and each one is exponentially distributed with parameter lambda I. So in other words, I have a bunch of independent lifetimes, xi independent. So in a queuing model, the x's could represent, some of them could represent the times until arrivals with Poisson input, and some of them could represent the times until departures with exponential service times. So what I want to ask is this. Suppose I look at the minimum. What's the probability that the minimum of these independent x's, what's its distribution? What's the probability the minimum is greater than t? To put it in another more simple context, suppose that these are service times. So this is the service time of server number 1, time of server number 2, and so forth. And so all of these servers, there are n servers, and they're serving their customers in parallel. And I want to know how long it takes until the first of those n service completions occurs. That's going to be the minimum of each of the service times. So what's the probability that the time I have to wait from now until the first service completion, minimum of these, is greater than t? Okay, now, the minimum, if the minimum is greater than t, then they must all be greater than t. So that's the same thing as the probability that x1 is greater than t, and x2 is greater than t, and so forth, up through x sub n. That's by the meaning or definition of minimum. But also, by assumption, these guys are independent. So the joint probability that they all last longer than t is the probability that, or the product of the probabilities, that each of them lasts longer than t. Okay, so this equal sign right here is because of independence. So far I haven't assumed anything about the distribution. Now let me use the assumption of exponentiality. Okay, so now I'm going to put this assumption right here. So now the next statement is that this product of probabilities is e to the minus lambda 1t times e to the minus lambda 2t, and so forth, e to the minus lambda sub nt. But now by ordinary arithmetic, that's the same thing as e to the minus lambda 1 plus lambda 2 plus lambda sub n t. So what that shows is that if I have a group of independent exponential variables, the minimum of those is also exponentially distributed with a parameter or rate that's equal to the sum of the individual rates. Okay, so here I have these lifetimes. Let's say there's variable 1, variable 2, variable 3, variable 4, and so forth, like that. And this one is an exponential lifetime, and its parameter is lambda 1. And that's an exponential lifetime, and its parameter is lambda 2, and so forth. And the question is, what's the distribution of time until the shortest one? In this picture, it would be that one right here. And the answer is, the probability that the shortest one is greater than t is e to the minus something t. So therefore, it's exponentially distributed. And the parameter of the exponential is the sum of the lambdas for each of the individual random variables. So if I have a bunch of customers in service and they have exponential service times, then the time until the next one of those service completions occurs is exponentially distributed. And its rate is equal to the sum of the service time rates for each of the individual customers. Question?
So even though their lifetimes are independent, their rates overall are dependent on each other?
No. The lifetime, these are independent random variables. Each is a lifetime which does not depend on any of the others. So this guy has an exponentially distributed lifetime, and his parameter is lambda 1. Actually, in queuing theory, they all have the same parameters, usually, but that's beside the point. This guy has an exponentially distributed lifetime. His parameter is lambda 2, and so on. Okay, now I want to ask, how much time do I have to wait until the first lifetime expires, until the first unlucky guy dies? How long do I have to wait for his death? That's going to be the minimum of the lifetimes of each of them. Now, according to this analysis, the probability at the minimum is greater than t has the mathematical form e to the minus something t. So therefore, since that's a probability of greater than is e to the minus something t, that's the definition of exponentially distributed. Now, what's the parameter of that exponential? Well, that parameter is the sum of the parameters of the individual lifetimes. The individual lifetimes are independent of each other, but the minimum is not independent of each of them. The minimum is the smallest one of all of them. So the time until the first service completion or the first death in this diagram is exponentially distributed, and its parameter, its rate, is the sum of the rates of each of the individual lifetimes. So minima of exponential variables are exponentially distributed. It's very important, because remember that what happens in a queuing process, in a birth and death process, is you've got this process of steps up and down. Now, what defines when a step occurs? Well, the step is going to occur when the next event happens. What's the next event? Well, it could be an arrival, it could be a departure. But if the times that between arrivals are exponential and the times between departures are exponential, then the times between events is the minimum of those exponentials, whichever occurs first. So how long is that going to last? Well, apparently it's going to be exponentially distributed. So if the individual lifetimes are exponentially distributed, then the times between jumps are going to be exponentially distributed, which means that the probability of having a jump in a little interval of length h is going to be proportional to h, and the proportionality constant is going to be the sum of the parameters of all of the processes that are racing against each other to make the process go up or down. It goes up when the race is won by a birth, and it goes down when the race is won by a death. So I'm trying to put all that together so that at the end we have exactly the postulates for the birth and death process. Then we'll know that as long as the underlying variables are exponential, the birth and death equations and rate up equals rate down describe the equilibrium distribution. Okay, so where we are now is we know that if we have a bunch of exponential variables racing against each other, we can look at it from the point of view of a race. Here's a race, and the length of time it takes for the person to win the race or to die first is exponentially distributed. And the question is, how long does the race last? The race lasts until the first guy dies. And if each of the lifetimes involved in the race is exponential, then the time until the first one occurs is also exponential, but its parameter is the sum of the parameters of all the racers. Okay, well, let me do a little, some more of these. Maybe this will start to make more sense. Remember, what I'm talking about now is basically intermediate level probability. Okay. So let's go back, keep this race analogy. Suppose I got two guys racing against each other. And by the way, this equation right here, this is equation 521 in the textbook, which is on page 46. So what we've shown, therefore, the min of these n independent exponential random variables is distributed as an exponential, but its rate is the sum of the rates of the runners. Now, suppose I look at two of them, and I ask this question. What I'm doing now is on page 48 in the textbook. Suppose I said this. What's the probability that if I have a race between two exponential runners, that runner number 2 loses to runner number 1. That is, what's the probability that x2 is greater than x1? If it's a race, then that means that x1 wins the race. He dies first. So depending on your point of view, I don't know, that might be winning, it might be losing. But in any event, what I'm asking is I'm going to compare these two exponential variables, and I want to know the probability that this particular one is shorter than that one, or this one is longer than that one. Now, obviously, by symmetry, if x1 and x2 have the same distribution, then this probability should be 1/2. But if they don't have the same distribution, well, it could be anything. Okay, so what's the probability that x2 is greater than x1? Well, first of all, I'll make the same argument I made before using the theorem of total probability. The differential of the distribution function of x1 evaluated at t. Now I'm using more advanced notation, but in the case in which the distribution function is differentiable, that means the density function at t dt. All right, so this is the probability now that interval number 1, that runner number 1 dies at time t. I'm going to multiply that by the probability that runner number 2 is still alive at time t, is still running at time t. That would be 1 minus the distribution function of x2 evaluated at t. And then I have to integrate that over all t from 0 to infinity. Okay, so I have this race between runner number 1 and runner number 2. This is the probability that runner number 1 finishes at time t, and this is the probability that runner number 2 has not yet finished by time t. So in other words, runner number 1 is less than runner number 2, so in this context he wins the race. Okay, what's that probability? Well, now I'm going to assume that x1 and x2 are exponential. So x1, x2 are exponential. And of course, we're going to have different parameters, because if they had the same parameter, then we could solve the problem by symmetry, because the answer would be 1/2. Okay, so now I just plug in the formulas for the exponential. This is going to be the density function for runner number 1. So it's exponential with parameter lambda 1. This is 1 minus the distribution function for runner number 2. Runner number 2 is exponential, so the probability that his race lasts longer than t is e to the minus lambda 2t. Okay, so this is general, and this is specifically for exponential. All right, now it's just arithmetic. So the way I'm going to analyze that, evaluate it, is I'll write that as an integral from 0 to infinity. I'll combine the exponentials, so I have e to the minus lambda 1 plus lambda 2 t dt. Then I have this lambda 1. I'm going to take that outside. That's that guy. And then I'll recognize that if I had a lambda 1 plus lambda 2 here, then this would be the density function of an exponential. And its density function would integrate out to 1. So I'll rewrite that as lambda 1 plus lambda 2 divided by lambda 1 plus lambda 2. Now, this thing, that integral, is equal to 1, because that's the integral of an exponential density function whose parameter is lambda 1 plus lambda 2. Actually, that's just a trick to allow me to evaluate this without doing any arithmetic. But I don't need that, because all I'm doing is integrating this thing right here. And when I integrate it, this is what I get. So this is a very simple result. It says that if I'm going to have a race between two exponential variables, the probability that runner number 1 wins the race is the ratio of his rate to the sum of the two rates. Actually, it's the simplest possible thing you could think of that might conceivably be the answer. which is the way the exponential works. Whenever you get an answer, if it's complicated, it's probably something wrong. Okay, so the answer is lambda 1 over lambda 1 plus lambda 2. How about the case in which the two runners have equal rates? The lambdas are equal. Then the probability is going to be 1/2, which is obviously correct. So it works for the boundary case, for the symmetric case. This is in the textbook. This is equation 5.23. Okay, so if we have exponential variables racing against each other, then the length of the race, the time for the minimum, is exponentially distributed with the rate equal to the sum of all the rates. And if we look at any two runners and we ask what's the probability that runner number 1 beats runner number 2, that probability is the ratio of the rate for runner number 1 divided by the sum of the rates for runner 1 and runner 2. So everything is just as simple as it could possibly be. Okay, so all of these properties of the exponential are kind of tying together here. So now I want to ask a more interesting question. But before I do I understand what's going on here? Don't get bogged down in the arithmetic. I mean, the arithmetic is something you should be able to do. It's straightforward elementary probability. But it's not the arithmetic that's the important point. The important point is that in the birth and death process, the process is generated by random variables that are racing against each other, arrivals and departures. And at any particular time, if the next event to occur is an arrival, then the process jumps up by 1. And if the next event to occur is a departure, then the process jumps down by 1. And we're assuming, because if we, as I'm going to show, if we assume that satisfies the postulates for the birth and death process and produces these answers, which we already have, that what we have then is the processes that are running against each other are exponential processes, because the times between arrivals are exponentially distributed by assumption if we have a Poisson process, and the times between service completions are exponentially distributed if we assume that we have exponential service times. So we have these arrivals and the service times racing against each other, and we're trying to understand what the distributions are of the times between the jumps up and the jumps down. And what it turns out is if the underlying variables are exponential, then the times between jumps up and jumps down, which represent minima, are also exponential. And so this exponential property just propagates, just stays there throughout the whole process. Okay, so now here's a much more interesting question. And what you got to keep thinking of, don't just think of this as being theory or queuing theory. What you're talking about is mathematical modeling and understanding what the consequences are of certain basic assumptions about probabilities. Okay, so what I want to do now is exercise 15 on page 49. And remember, all of these exercises are done in detail in the solutions manual. And now we want to ask this question. Suppose we have these two guys racing. These are exponential guys. And we want to say, what's the probability that the minimum of x1 and x2, that is the time the race takes, what's the probability that the race takes longer than t if I know who the winner is? So if I don't know who the winner is, I know that the minimum is exponentially distributed. But now I'm going to tell you I got this race, and I got two guys racing, and I'm going to tell you who won. Now, if I tell you who won, what does it tell you about how long the race took? Well, of course, it depends on who won. If the fast guy won the race, what does that tell you about how long the race took? If the slow guy won the race, what does that tell you? If I know the slow guy won the race, did the race take a long time or a short time? You could argue that, well, if the slow guy won the race, it must have taken a long time because he's slow. You could argue no, it must have taken a short time because if the slow guy won the race, he must have really been running fast because he ran faster than the fast guy. So which is it?
Neither.
What is it?
Neither.
Neither. Well, okay, we're going to show that these are independent random variables. So we have a race, and knowing who won the race doesn't tell how long the race took, surprisingly. Okay, so this is now an exercise in probability to show that this is true. But this will turn out to be important in our proof that when we combine all of this stuff, that we get a birth and death process. Okay, so what's this probability? Well, the probability of these events occurring jointly, the conditional probability, the denominator is the probability on which I am conditioning, and the numerator is the probability of these events occurring jointly. That is, that the race lasts longer than t, and the winner is runner number 1. Okay, what are those probabilities? Well, the probability that x1 is less than x2, we already worked that out right here. It's given by this integral. So let me write the integral. We already know what it is, but I'm going to write it as an integral. It's the integral from 0 to infinity of 1 minus the distribution function of x2 evaluated at t times the differential or the density function of the distribution function of x1 evaluated at t. Okay, so what is this? This is the probability that runner number 1 finishes his race at time t, and this is the probability that runner number 2 takes longer than time t. So therefore, it's the probability that runner number 1 is less or wins the race over runner number 2. Now in the numerator, I want the equivalent probability, but with the additional condition that the minimum is greater than t. Well, obviously, once I write it down, it's the same as the denominator, except for the lower limit. So here is the probability that runner number 1 ends his race at time t. Here is the probability that runner number 2 takes longer than t. And I integrate that over all t, excuse me, I should have written u here. Yeah, I screwed up because I got my t's mixed up, which I always chastise undergraduates for, because I want to use t both here. So I want to use it here. I can't use it as the parameter here. Okay, so here, this is the probability that runner number 1 beats runner number 2. And this is the probability that runner number 1 ends his race at time u. Runner number 2 takes longer than u, but u is at least t, because I have to have the condition that runner number 1 beats runner number 2 and the minimum is greater than t. So the numerator differs from the denominator by having this t right here as the lower limit. But now this is easy. We've already done the denominator. Okay, let's see. The denominator, the answer was lambda 1 over lambda 1 plus lambda 2. The numerator, I can write exactly the same way. I'm going to get lambda 1 over lambda 1 plus lambda 2 integral from t to infinity, rather than from 0 to infinity, of lambda 1 plus lambda 2 e to the minus, I should give myself more room here. Okay, I've got to move this numerator up. Okay, so this is, I'm writing this integral right here. I have an integral from t to infinity. Let me see if I get one of these that writes. Again, t to infinity. Okay, now, this numerator, put him over here. Integral t to infinity. This is lambda 1 e to the minus lambda 1 u du. And as before, this is e to the minus lambda 2 u. And what I do is I take that lambda 1 outside, so he's gone, and then I put a lambda 1 plus lambda 2 in here and divide by lambda 1 plus lambda 2 there. This guy cancels with that guy, and what I'm left with is this. But what is that? That's the integral from from t to infinity of lambda 1 plus lambda 2 e to the minus lambda 1 plus lambda 2 mu, or u, du. But that's the integral of an exponential density function whose parameter is lambda 1 plus lambda 2. In other words, that's the probability, as we've already seen, that the min of x1 and x2 is greater than t. So what I just proved was that the probability that the min is greater than t, knowing who won the race, is exactly the same as the probability that the min is greater than t if I have no information about who won the race. Which means that the length of the race and the winner of the race are independent of each other. Very strange. Okay, now why is that? Well, it has something to do with the Markov property of the exponential distribution, obviously. Because in any other case, if I plug into this formula right here, I'm not going to get that cancellation. It's not going to be true that the identity of the winner and the length of the race are independent of each other. Okay, I'm going to start here next time, and I'm going to give an intuitive argument for why this is true, at least for the exponential. And of course, it'll be based on the Markov property. Because once you know what you're trying to get at, then there's usually a way to get at it using the Markov property without going through any arithmetic. But I didn't want to do it that way because that would be too clever. So I just did it by brute force, and I observed. So you should go through this and make sure you understand the arithmetic. I observed that if I calculate the conditional probability that the race lasts longer than t, given the identity of the winner of the race, I get exactly the same as if I didn't know who the winner was. So therefore, the length of the race and the identity of the winner